Lab 2, Motion of a Falling Object. The purpose of Lab 2 is to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down, using Newton's second law. In order to do this, I dropped a small empty cereal box, adjusted the parameters, and observed its position versus time data in Tracker. Then compared this observed data to a series of computational models, one which compensated for the weight force on the object, and one which compensated for the weight force and the drag force on the object. My findings were that without compensating for the drag force, the computational model overpredicted the final position of the cereal box. First, in observing the falling box in Tracker, I adjusted my axes to tilt at a slight angle so that the box would fall along the y-axis, and I set the calibration stick to the length of the box, 14 centimeters. The position versus time data obtained from Tracker shows an increase in velocity as time goes on. Therefore, we know that since velocity is not constant, Fnet cannot equal 0, meaning that at least one force from the surroundings was acting on our system. In the first computational model, the initial parameters were set according to the observations made in Tracker. The mass of the object was set to 0.00438 kilograms, the mass of the empty cereal box. The initial time was set to 0. The initial position was set to negative 0.001 meters in the y component, and the initial velocity was set to 0 because the object started at rest. Then, to calculate position and velocity while time is less than 0.635 seconds, according to Newton's second law, knowing that Fnet does not equal 0, I set Fnet equal to the weight force, negative mass times g, 9.8, times j hat, in the vector form. Then set the ball position equal to ball.pos plus ball.vel times delta t, and ball.vel equals ball.vel plus Fnet over n times delta t, both according to Newton's second law. The data from this computational model was way off from the observed data. It greatly overpredicted the object's position. So, we know that there must be another force acting on our system to keep the box from going that far that we have not accounted for. In the second computational model, we accounted for this overprediction by adding in the drag force, or air resistance, on the falling cardboard box. In order to do this, in the code, we change Fnet from just equaling the weight force, W, to equal the weight force plus the drag force. The drag force we know is negative B times V. In order to determine what B should be, I tried logical guesses for B in the code until the final output was as close as possible to the final position of the box observed in Tracker of negative 0.228 meters. This value was B equals 0.115 Newton seconds per meter. The yellow arrow represents the weight force coming down off of the object, and the blue arrow represents the drag force pointing in the opposite direction of the object's movement. The output of this computational model can be seen here in orange, matched much more closely to the experimental data, which is the blue dotted line, because the net force was a lot closer to the actual net force on the system by the surroundings. Terminal velocity is when the drag force starts acting enough on the object that it stops accelerating, thus has constant velocity. The first computational model has no terminal velocity because its parabolic shape indicates the object continues to accelerate. This makes sense because the model did not account for the drag force. The experimental and second computational model data show terminal velocity from around 0.45 seconds to 0.635 seconds, or the end of the run. This makes sense because the drag force exists in the experimental data, and the second computational model accounts for drag force, slowing down the object's acceleration to terminal velocity before it lands. The drag force is equal to negative B times V, so the drag force would have a larger magnitude if the object's initial velocity was not 0, and the drag force arrow seen earlier, the blue one, would have been bigger. And the gravitational force, negative mg, will be the same if the object was thrown downward than if it had started at rest, because the object has the same mass. Therefore, terminal velocity of an object thrown downward with an initial velocity will be the same as an object dropped from rest. In conclusion, the model with drag force and weight force almost perfectly maps to the experimental data. It just slightly overpredicts. Possible sources for error in this include arbitrarily guessing and checking for the B constant, and the mass of the cardboard box was very light, and there was also wind blowing whilst filming the experiment outside, and you can see it as it goes back a little bit in the z-axis direction from the y-axis. All in all, Once weight force and drag force were accounted for, the model matched up to the experiment.